Hey y'all, my name's Aurod, that's Cade, and that's Westen. We're here today to talk about the Deepwater Horizon oil agglomerates, which was problem A for SCUDEM 2020. And we are team 1072, and we are from Tarleton State University.
All right, so like Aurod said, we chose problem A for this year's SCUDEM challenge. And so it starts with the Gulf Coast when there was the Deepwater Horizon explosion at the oil rig, where millions of barrels were dumped into the ocean. This explosion caused lots of oil to agglomerate and eventually end up on the shores of Florida. What we're calling sediment oil agglomerates were formed, and it is observed that years later that microbial decomposition and biodegradation occurred, and they were thoroughly buried underneath the beach sands. And so the problem that we're addressing is we're trying to model the decay of the mass of the SOAs using just regular differential equations.
So for our assumptions, we got them all from the first paper listed within the competition. And the first assumption we're making is that the decay rates that they give are for the chemical concentrations. And within that paper, it lists that they account for the depth at which the SOA is buried. Also within that paper, it lists the average size of a pore, average radius of a pore in the sand, which is about 2 millimeters. The SOA itself, the clump of oil, that average radius range anywhere from a half to 2.5 centimeters. Then the SOA, the two main chemical compounds made up of it were the alkanes and the PAHs. The alkanes were comprised of petroleum hydrocarbons and other carbon content, which those two decays were given within the paper one as well. And the PAH is made up of 16 of the US EPA priority compounds, and as well as 11 additional PAHs.
So as you can see on the right of this slide, you can see our 13 parameters. 4 of these parameters are equations, and all 4 of those equations are exponential decays that were given in the research paper that we referenced. They were all the petroleum decay rate and the carbon decay rate, as well as the pH concentration and the alkane concentration decays, are all the chemicals that can be found within the oil within the SOAs. So we used these parameters for our ordinary differential equations that you can see on the left-hand side of the screen. Our first differential equation is for the total mass, and our second differential equation is for the mass loss of the sand, the oil, and just the SOA in general. So within the mass loss differential equation, you can see that the first two terms are the petroleum and the carbon decay rate added together. You multiply that by the time that whatever the time you have in your at that moment, then you have the alkanes plus the pH decay rate, concentration decay rate, those added up together, and you multiply all of those by the initial mass. This will give you the portion of the initial mass at that specific time that you have that is being lost at that consistent rate. You multiply that by the porosity, and that gives you your overall mass loss, because the porosity pretty much tells you how quickly the masses of the chemicals are being reduced, dependent on all the 4 equations that were given in the parameters on the right side of the screen. The top equation, which is the total mass, you can see that it's the porosity divided by the initial mass. This will give you the overall oil mass, neglecting all of the sediment that has been that has surrounded it. And from that, you subtract the mass loss times the mass initial, which gives you a number in kilograms of mass that has been lost in that specific amount of time that was identified in the mass loss equation. And of course, these equations are a coupled system of differential equations. So for our results, as time goes on, we noticed that the mass loss gradually increased, and with that, the total mass was slowly decreasing, showing a negative relationship between these two parameters and the differential equations. Using the data that was given in paper 1, which you can actually see on the right side of this slide, you can see that in graph A, you have the decay rate of the petroleum hydrocarbons, which was gamma. We don't really need graph B. And graph C shows you the carbon content, which was, as you can see back here, it was your alpha, not your alpha, but your sigma. And then D shows you the decay rate as depth goes down or up in the sand. So that it takes into account the sediment depth. And we noticed that in the model and research paper 1, there was the chemicals decayed at a slower rate than the overall mass of the SOA. The reason for this is because the SOA is comprised of sediments as well as the chemical that was in those agglomerates. That's why the decay rate is a bit slower in our model. And the overall mass decays at a slower rate than the chemicals, as I mentioned previously. And for our time rate, we used about the same thing that the researchers in the research paper 1 used, which is around 3 years, and to be specific, 1,152 days was the end of their experiment period. So we used that, and we saw that there's about a 20% total mass loss, as you can see in our code, which I'm about to show you. So this is our code. We have our definition of our parameters, the definition of the equations that I mentioned earlier on, and the definition of our ordinary differential equations, the coupled system, the integration of those ODEs, and then the plotting of our results. So as you can see, this is the plot of the results that would come from the research paper. So we used the 33.7 grams of SOA, which was about the average, and it shows that there's like a very slow decay of the total mass, while there is a very gradual mass loss that is increasing, which results in the total mass decreasing. If you were to raise the amount of SOA that you have to about 50 grams, and I would change it down here as well, you would see that the graph decays much quicker as there's more surface area to the SOAs, meaning more porosity, there's more chemical, but more chemical to be decayed, and the mass loss increases about at a similar rate. So going back to the presentation, we will get to the next slide.
So on top of modeling the mass decay rate of the SOAs, we had 2 additional problems asked for us. One was removing a small top layer of sand from the beach, and this would put the SOA at a more shallow part of the sand, meaning that it would move up into the sand, and then the chemical compounds would actually decay much faster. This brings them up out of their ideal decreasing rate, which was mentioned in research paper 1. And with them moving up, the sand is less dense, meaning more oxygen and more water can come in contact with the SOA. And this is going to increase the microbial decomposition and biodegradation. And as far as the overall mass result, it would also increase the decay rate much more than if it was buried deeper within the sand. And then for the second additional problem, we were asked to estimate the time for the SOA to only be down to 10% of its mass. And basing off of our graph and our code, over about 3 years, we lost 20%. So basing it off of that, we got to where it would be roughly 16 years or 6,000 days.
So our overall conclusions are that we found that as the initial mass of the SOA increases, the rate at which the mass is lost also increases. So the result agrees with the research paper that was given to us with the problem, as the rate of which mass is lost is similar to the decay rate of the chemical compounds. In the future, we're looking to spend more time refining the program that we already have coded. We're hoping to use a different coding platform to find the equilibrium points using other methods that we've wanting to find, obviously. And we hope to refine the program that we have so we can fix the increase in mass at the beginning. So, and these are just our references that we've used, and that's pretty much everything. So thank you.